Welcome to Dr. Jed's continuing series on calculus videos. This section is 3.6 from Rogowski, the derivatives of trigonometric functions. Now before we go on, I want to point something important out. We are only going to be talking about trig functions in radians. This is very important because in degrees or other units, the formulas don't work out nicely. In radians, they do. Now, it is possible to do it in other forms, like degrees. And later, when we learn the chain rule, we can learn how. For now, it's all radians. First, we're going to find the derivative of cosine, then the derivative of sine. Then we're going to put them together to get all 6 of the trigonometric functions. And then we're going to do some examples. So first, cosine. Now, to find the derivative of cosine, we'll go back to the limit definition. The definition of the derivative says it's the limit as h goes to 0 of f of x plus h minus f of x all over h. Now, the thing about trigonometric functions is how you break this apart. There's a rule for cosine of a plus b. It's kind of messy, but what it is the cosine of a, or in this case x, times the cosine of b, in this case h, minus the sine of the first one, times the sine of the second, and then we still have that minus cosine of x on there dangling. Now this may look like a lot of mess, but we can factor pieces out and clump it together. This first one and the last one both have a cosine of x in them. So if I rewrite this, I'm going to actually just write those two over h. So I have cosine of x, cosine of h minus the cosine of x all over h. The other piece, this minus here, this is also minus the sine of x, sine of h over h. Now, that doesn't necessarily look a lot better, but if I factor a cosine of x out of here, turn these into two separate limits, then what do we have? I have the limit of cosine of x times the rest of this. Factor the cosine of x out. I have cosine of h minus 1 over h, and then minus the limit as h goes to 0. Pull the sine of x out the same way. And the nice thing about this is cosine of x, for symmetry there, cosine of x has nothing to do with h. It's constant relative to h. Likewise, the sine of x is. So let me pull those out. It's fairly tedious to write this out, but once I'm done, you will hopefully see things you remember. This is a limit from before, when we did limits, trigonometric limits. This limit and this limit were the two limits we studied. So this is one of the reasons why we did. They're useful limits, they're easy to use, but they're really important right here. This one, right here, was 0. So we get cosine of x times 0. This one, right here, was 1 minus the sine of x times 1. 0 times anything is 0, minus sine of x times 1. I get minus the sine of x. So that's the cosine's derivative. Next, let's do the sine's derivative. I could do it the same way with the same kind of formulas, but I want to actually try a different approach. I want to start with the Pythagorean identity. This is something that's just very basic to trigonometry. So sine of x squared times the cosine of x squared, regardless of what x is, it's always 1, right? This plus this is always 1. This is just 1. So that means the derivative of this would be the same as the derivative of 1. That's a little weird. We're not doing it directly. We're saying this is that. They're the same thing. So that means the derivative of this is the derivative of that. Now, the derivative of 1 is easy. It's 0, because 1 is a constant. The derivative over here, well, this can be tricky. But I've written sine squared of x as sine times sine, so we can use the product rule. This is the sine times the sine, the first times the second. The derivative of that is the derivative of the first times the second, plus the derivative of the second times the first. Now notice those are the same thing. The derivative of the first, we don't know what that is yet, times the second, plus the derivative of the second, times the first. Now I'm not going to have enough room in here, but notice these are the same thing, right? So there's two of them. So I'm going to just write 2 times for this one. The derivative of the first or the second are the same thing. Then we just learned the derivative of the cosine is the minus sine. Times the other one, the cosine x. Now, it may not look right nice, but I'm going to rewrite this. There's a minus sign in here, so I'm going to pull that out. So look at this. 2 sine x times something minus 2 sine x times cosine of x is 0. So again, 2 sine x times, we don't know, minus 2 sine x times cosine is 0. There's only one way that works. Now if sine of x is 0, both of these are 0. That's great. But sine x is not always 0. So to make this always work, we need the sine prime to be cosine. So the derivative of sine of x is the cosine of x. And again, just to refresh you, and just to remind, we're always in radians here. If we're in degrees, this is not going to work. So I've written this one and the previous one over here on these top two. I've also written the other ones. We have the derivative of sine is the cosine. The derivative of cosine is the minus sine. Notice there's a pattern in there. It's not completely symmetric, but it's interesting. And then the tangent of x is the sine of x over cosine of x. If you do the quotient rule and simplify, you get the secant squared of x. The derivative of secant of x, it's a quotient also. You get the secant of x times the tangent of x. And there's two more, the cotangent of x and the cosecant of x. Their derivatives are respectively minus the cosecant squared of x and minus the cosecant of x cotangent of x. Notice there's a relationship, a pattern sort of. Sine is positive cosine, cosine is minus sine. So one of them is positive, one's minus. The tangent, secant, both have positives. The cotangent, cosecant are the same kind of things, but both are minus. So let's take a look at this. Here's an example. I want to try something very far-fetched. I want the 80th derivative of the cosine. You think, well, that takes a long time. It actually won't take that long, because what is the first derivative? The derivative of the cosine is, we just learned it, minus the sine x. What's the second derivative? What's the derivative of that? But that's just minus the cosine, so its derivative is minus the derivative of the sine. So it's minus the cosine. What's the third derivative going to be? It's going to be, well, minus the cosine. The cosine's derivative is minus sine. The minus is like a minus 1, which we can just pull out. So we'll have a minus minus. So we'll have a plus the sine of x. The plus is probably optional, but I just wanted to emphasize that. And the fourth one. What's the fourth one? It's the derivative of the sine of x. And that derivative, we learned, was the cosine of x. Now, we could keep going, and we could do it 76 more times. But that's kind of silly. Notice, the function was the cosine of x. The fourth derivative of it is the cosine of x. So that means the fourth derivative of this, which is the 8th derivative, will be the cosine of x. The 12th derivative, the 16th. And if you see every multiple of 4, the derivative will be the cosine. So therefore, the 80th derivative of the cosine of x is just the cosine of x. Now from here, I can introduce the concept we talked briefly, I think last time, about differential equations. We have this is the same as this. We could actually say this differential equation has cosine of x as a solution. Why? Because this is the cosine of x, this is the cosine of x. Cosine of x minus cosine of x is 0. It's a pretty large number to put in a differential equation. It's most common to find them with first order with only first derivatives, or second order with second derivatives in there, or maybe even a third order sometimes. That's about as far as you usually get, but we can do it. It works. Let's take another example, though. More mundane. What's the squared sine of x going to be? Well, the derivative of x squared sine of x, this is the product rule. I didn't write it that way before, but off of the product rule, we write f and then g. Just because it's easy to organize, we get f prime and g prime, the derivative of these. So the derivative of x squared is 2x, and the derivative of sine of x is cosine of x. Remember, the product rule is f prime times g plus g prime times f. So it's f prime times g plus g prime times f. If I write it that way, I'm going to show you. If I write it that way, this is a little awkward. So we usually put polynomials in front of the trigonometric function. So let me rewrite that. And there's our answer. Can you factor out of that? You can factor an x out of that. That's about all. And I don't really know how useful it is. Remember, simplification, the goal is to make it simpler. And if you pull an x out, that's not really any simpler. So this is how you use the derivatives. Now, one last bit. Let's do another tangent line. Tangent line to tangent of x. Oddly enough, we're taking the tangent of tangent. But at x equals pi over 4, well, the derivative of the tangent, we learned, is the secant squared of x. That's not that useful. That's the instructions for the slope. It's not the slope itself. To find the slope, we plug in our x value. You have to think back, perhaps, but the secant is 1 over the cosine. So this is 1 over the cosine squared of pi over 4. And the cosine of pi over 4 is square root of 2 over 2. So we get 1 over, that's square root of 2 over 2 squared. Well, if you think about that, that's 2 over 4, which is 1/2. But 1/2 on the bottom is 2. So the slope is 2. We have y equals 2x plus something. Now that something is not going to be super pretty this time, because we know x is pi over 4. And the y. Well, to find the y value, we plug x back into the original. And the tangent of pi over 4, think back, is 1. 1 is, well, what is that? 2 times pi over 4. 2 pi's over 4 is pi over 2. We have pi over 2 on this side, we have 1 on this side. To balance that out, we should have minus pi over 2 plus 1. Why? Because that'll turn into 1. That's our y-intercept. Now pi over 2 is, let's say, 3.1, so it's about 1.5-ish. So minus that plus that, we got about minus 1/2. So let's take a look at the curve. If this is a slope of 2, does that look like it's about minus 1/2? I think so. It's not the best curve in the world, but there you can see the tangent to tangent is that. Until next time, this is Dr. Jett.